Did you, like me, ever wonder why there are multiple formulas for the empirical variance? This version shown here is probably the one you encountered first. Next, when you moved on from descriptive statistics to inferential statistics, you probably got introduced to this version, where you have n-1 instead of n in the denominator and x bar instead of mu. So why is this? You might get answers like, when you estimate the sample mean, you don't divide by the sample size, but by the degrees of freedom, which actually does not explain anything. However, there's an important bit of information hidden. It basically says, because you have x bar instead of mu, you need the n-1. This is called Bessel's correction, and in today's video I want to provide an intuitive understanding why there's this correction and why is it exactly this correction and not a different one. I think this is also why so many people are interested in this question. First, it feels weird and counterintuitive that the correction has nothing to do with the last part where the x bar is, but somehow with the first part, the number of data points. On the other hand, it feels like it should have a plausible explanation because it does not seem to involve much math. No fancy Greek letters, no other sums or integrals, just subtract 1 from a sample size. Done. However, a satisfying explanation to that is seldom taught. Often you will get hand-waving explanations instead, like the one with the degrees of freedom, that are correct, but also not very helpful. Before we dive in, let's clarify some basic terms. The empirical variance is a measure of spread of data points. The more spread out your data points are, the higher the variance gets. Because of the square, it gets even bigger with increasing spread. The variance formula consists of 3 parts. First, you calculate the distance between every data point and the mean and square it. This gives you a list of square distances. Note there's a 0 because one of our data points happens to have the same value as our mean, so the distance from this data point to the mean is 0. Next, you add them all up. The result you get is sometimes also called the sum of squares or sum of square differences or distances. More frequently, it is discussed in the context of ANOVA or regression, but is basically the same thing. As you can see here, this term has a very literal meaning. You can simply use areas for calculation. Next, you divide this sum by the number of data points. Doing so, you get the average squared distance of the data points from the mean. And that is all there is. This is your empirical variance. You might ask why people use the squared difference and not the absolute value or a power other than 2. These are reasonable questions, but I will not go into detail about that here. All I'm going to say is that this expression has 3 important properties. First, after applying the square, all values are positive, so nothing can cancel out when you add up the individual terms. It does not matter if data points are smaller or bigger than the mean. Next, bigger differences have a bigger influence on the result due to the square. And third, this is mathematically just a bit easier to work with than with absolute values. Now let's come back to our initial question. Why do we use our n here, 7, instead of n-1, 6? The reason is you use n-1 if you don't have access to the population mean and have to estimate that in addition to your variance using the sample average x bar. This is true for probably most experimental setups where you draw samples. There can be 2 scenarios in which you can use the formula with n in the denominator. The first is if you have access to the whole population. Then you can simply calculate mu and use it to calculate the variance. The second is if you only have a sample and want to estimate the population variance, but you also know the population mean. This is rare, so it is usually a good rule of thumb to memorize that you use x bar and n-1 when you estimate the variance based on a sample, and mu and n when you have access to the whole population. As a side note, the official term for what I call population value here is a parameter, while a sample value is a statistic. To make things a bit easier, I will continue to use the terms population value and sample value for this video. What happens if you insist of using the formula with n in the denominator for estimation using x bar? Well, chances are your estimation of variance will be too low. Let me explain that in more detail. First, you will need to find the right mean to plug in into the formula. Let's say you don't have access to this population of 7 members and no one told you the population mean, so you need to draw a sample and estimate the population mean based on that. Let's say data collection is very costly, so you decide to take a sample of 3 members. You can easily imagine that your sample mean might be different from the population mean. For example, just by chance, you might draw the 3 lowest numbers from our population, and your sample mean as a result is smaller than population mean 5. However, it is equally likely that you draw the biggest 3 values from the population. Then your mean will be bigger than population mean, and exactly by the same amount the first sample mean was smaller. Of course, you cannot know this because you don't know any other value apart from your sample. That you normally don't worry about this and just report the sample mean without any correction is because the sample mean is an unbiased estimator for the population mean. Unbiased estimator means that on average, in the very long run, your estimated mean will equal the population mean, even though your individual estimation might be wrong. Let's see how this looks like. Imagine that you draw multiple samples from your population and calculate the mean for all these samples. You could then count how often certain means occur. In this population of 7, the smallest possible mean with a sample of 3 without replacement is actually 2, as seen before, and you have to sample all 3 smallest values to get this. A mean of 5 instead is more likely. You can draw 159 or 258 or 357 to get there. You could do this for a much bigger number of samples and draw something like a histogram. This would be the distribution of sample means. Here you see a smooth version of this that is not to scale, but it transmits the concept. You see that more extreme values are less likely because you have to draw all extreme values to get them. You see that this distribution of sample means is symmetric and has its peak where the population mean is. Higher means are as probable as lower ones, and values closer to the population mean are more likely than extreme values. What will also happen is that with increasing sample size, this distribution will become narrower and values close to the population mean will become even more likely. You can easily see why this is the case. In the last example, the smallest mean with a sample of 3 was 2. Now imagine a sample size of 4. You will have to draw the 3 smallest values as before to get there, shown in yellow, but also the 4th smallest value, in this case 5, shown in red. By definition, this is bigger than your other 3 values, so your mean will increase. The smallest possible sample mean will now be 11 divided by 4, which is 2.75. Sometimes you will hear that the sample mean will, in the expectation, equal the population mean. But this is just the same as saying that in the very long run, when you average all results, the 2 values will be the same. We will come back to this distribution later, but let's first see how that looks for the variance when you plug in x bar that we calculated in this step. Actually, it looks quite different if you use the uncorrected formula in the wrong circumstances. Now you are more likely to underestimate the variance than to overestimate it. That does not mean that you always do. It just means there are more possibilities for underestimation, and the most probable value now is not the population value, but a smaller one. So the solution to this issue is, as you might have guessed by this point, to use Bessel's correction. When you make the denominator smaller, the overall value will be bigger and the estimator will now be unbiased. If your education is like mine, this is the first challenge to understand when going from descriptive to inferential statistics. Let's examine this in more detail. At this point, we have 2 questions to be answered. First, why is the variance formula with n and x bar biased? And second, why is everything fine when we divide by n-1 compared to any other value we could think of? n-1 sounds utterly simple but also specific, so what is the reason for that? I will give you 2 explanations for these questions, and I hope that makes the correction more intuitive for you. One involves the formula with the sample mean that you probably know. The other one involves pairwise differences, which I will introduce later. By the way, I don't talk about any secrets here, so I will give you a few links in the description where these issues are presented and discussed. Let's start with the first explanation involving the sample mean. Why is the formula with n biased? Why does the values you calculate tend to be too low? To answer this, we look at the data example from earlier again. These are the same values, I just shuffled the order a bit, but you see that the variance, the average squared distance of values from the mean, is the same as earlier, 8.29. Also note that this is our population, so we calculate the population variance using the population mean and n in the denominator. Everything fine. Now, the mean has a special property within this formula. Using the mean will give you the smallest result possible. This means that when I plug in any other value where currently the population mean of 5 sits, the result will be bigger than 8.29. Another way of saying that is that the points from your sample will tend to be closer to the sample mean than to the population mean. Let's try a few different values. So 9 is absolutely not the mean of the population, and see how the result increased to 24.29. Let's try a smaller value than 5 now, which is also closer to 5. The result is still bigger with 12.29, although not as big as before. Let's try a value very close to 5, 4.9. It's still bigger with 8.3. And a value that is a bit bigger than 5 also leads to a bigger value. This is of course no mathematical proof, but I don't want to get into too much detail here because it is not the main focus. I think it is enough if you get an intuitive feel that the mean has this special property within the variance formula. When you graph different values, you will see that they will form a parabola with a mean corresponding to the minimum value. On the x-axis, you see the different values you plug in, and on the y-axis, the result that the formula gives you. You cannot get a smaller value other than that which you get using the mean of 5, which is 8.29. This is also our variance. Now, why is this a problem for our estimation of the variance when we only have access to a sample? Let's see what happens. We will draw samples of 3 and put the sum of squared differences right next to our normally unknown population values. You can think of it this way. Each value of the data has a correct distance to calculate the variance, the distance to the population mean, which is the left column. However, because you normally only have a sample, you need to use the sample mean and calculate the distance to this value instead to estimate the variance. This will be the right column. The first sample is 5, 9, and 7 with a mean of 7. The squared differences to the sample mean are 4, 4, and 0. Note that they are different from the values you get when you use the population mean, which are 0, 16, and 4. Now, it might be not surprising that they are different, right? We saw the same for the mean earlier, where there was variation as well. However, for unbiasedness, it must be equally likely to get smaller values and to get bigger values. This is not true here. Why? Because the property that the mean minimizes the variance formula also applies to samples and the sample mean. Using the sample mean will minimize the result within that sample, and the variance using the sample mean will thus on average be too small. Again, another way of seeing it is that the sample data points will be closer to the sample mean than to the population mean because it is designed so that the variance is minimal. That can be a bit to chew on, so let me spoil the conclusion here before I show you more examples. Whatever sample you draw, the sum of the squared difference to the population mean, in this case 20 in the left column, is an upper bound to the sum of the squared differences to the sample mean in the right column, in this case 8. The latter can never be bigger than the former for any sample, and this is where the bias comes from. Individual differences can be bigger, like in this case for the sample value 5, but these are then offset by other values so that the sum is equal or smaller. Let's use a different sample, 3, 5, and 8. You see that it's closer this time, but the sum of the values using the sample mean, 12.67, is smaller than the sum of the values using the population mean, 13. Let's do one more, 9, 7, and 2. Again, the sum of squares in the left column is bigger than the right column, 29 to 26. However, when you calculate the variance, the estimate will be too big. It doesn't even matter if we use Bessel correction or not. You will get 26 divided by 3, which is 8.66, which will get even bigger and thus quote-unquote more wrong with Bessel's correction. Is that a contradiction? Actually, it is not. It arises because the sample happens to be very spread out. This is an example that you can overestimate the variance even without Bessel's correction. It is just less likely to happen. It is the same issue that arises when you want to estimate a population mean. Some samples will have a larger mean, some will have a smaller, but on average, after an infinite number of samples, the mean will equal the population mean. Important for our discussion of bias here is that the sum of the values in the right column is smaller than the sum of the corresponding entries in the left column. So I said earlier that the sum of squared differences to the population mean is an upper bound to the sum of squared differences to the sample mean. Up until now, we only saw examples where this meant that the latter was always smaller than the former. When can they be equal? Only when population mean and sample mean are the same. Look that in this case here, where I drew the sample 3, 5, and 7, the individual contributions are the same, 4, 0, 4, because the two means are the same. As before, that does not guarantee that your estimation of variance will be correct. It is not. It is smaller than 8.29, but only that the individual contributions are not biased. Also for this sample, the sum of squared differences to the population mean is the same as the sum of squared differences to the sample mean. However, again, only the individual parts are correct. The calculated variance will be too big. You see the pattern here, but let me state it. When the sample mean equals the population mean, the sum of squared differences will also be equal. The variance that you calculate based on the sample, however, can individually be too small or too big. And because any sample with a mean different from the population mean will lead to a sum of squared difference that is too small, this formula for the variance shown here is biased downwards. So what are the core issues? First, your sample mean varies and is almost never equal to the population mean. We saw earlier that it is unbiased, but it still varies from sample to sample. Second, when you plug in the sample mean in the formula for the variance, this will minimize the result. This in turn leads to the fact that the sum of squared differences to the sample mean is always smaller or equal to the sum of squared differences to the population mean. Third, all of this leads to an underestimation of the variance in the long run, a bias. Now that we tackled the first question, why do we have this bias, let's talk about the second. Remember that putting n-1 in the denominator does not just make the formula a bit better in some way, but it will actually make it unbiased. First, we know that we will introduce a bias when we just plug in the sample mean in the variance formula because the sum of squared differences to the sample mean for a given sample can only be equal or smaller than the sum of squared differences to the unknown population mean. Thus, we know there should be a difference between the formulas and the expectancy. This is the bias. We can formalize this. Let's call the first term sigma squared, which is the official symbol for the population variance, by the way, and the second one, the one with bias, as n squared. Now, because we know there is a difference in the expectancy, the bias, we can try to find that. First, we plug in our formulas. That starts to look a bit complicated, but you will earn a satisfying solution in the end, I promise. If you don't like all these formulas, you can just skip it and hop back in when we discuss the solution. The first thing we notice is that we have binomial formulas which we can solve. We plug in these results to get this expression. Now we are allowed to combine the sums because I and n are always the same, and we divide each element in both sums by the same number n. Note that this is exactly the same expression as before, just without the second 1 divided by n and the second sum symbol. Now we rearrange a bit with the goal of placing everything that does not depend on the sum outside of it. We are allowed to do that because it is the same to multiply each term of a sum with a constant or only the result of the sum. The xi squared here, which is not in blue, cancels out. Now, mu squared minus x bar squared does not depend on I, so we can put it outside the sum. Now we can also remove 2 times x bar minus mu from the sum so that only xi remains within it. Now that's cool. The last part is just the sample mean x bar. You add all values and then divide by n. So let's put that in instead. Then we can solve the second part. Then we can rearrange what we get once more. So you might see that this is just a binomial formula again that we can factor to get this result. the expectancy of x bar minus mu squared. Do you recognize this term? It is actually the variance of the sample mean. And this is the same as the population variance divided by the sample size. Isn't that cool? We said earlier that one of the core issues of the bias in estimating the variance is that the sample mean varies from sample to sample, and here we have it. The expected difference between the correct formula of the variance and the wrong one with n and the sample mean is equal to the variance of the sample mean. Now we are only one step away from solving the n-1 conundrum. We can rearrange this equation and find how both kinds of variance, the correct one and the biased one, are related. We find that the formula with n in the denominator and the sample mean underestimates the true variance by the variance of the sample mean, which is the variance of the population divided by the sample size. We can rewrite that as, drumroll, n-1 divided by n times the population variance. With this information, we can calculate a correction factor for Sn squared, which is basically just the inverse. That means we get an unbiased estimator when we multiply the biased estimator by n divided by n-1. This, however, is equal to this expression, and as you might see, the n cancels out, so that we get our final formula with n-1 in the denominator. Nice! So what did we learn? The root cause for the bias is that the sample mean varies and that the sample mean will minimize the sample variance. We can correct for the bias when we calculate how big the introduced difference is and then apply the correction factor. That this happens to be n-1 is because the variance of the sample and the variance of the sample mean both depend on the sample size. It does not have anything to do with using one observation less. Okay, now I promised you 2 explanations, so let's dive straight into the next. I'll make use of a different formula for variance that I will introduce in a second. This might be new and uncommon for you, but it brings the advantage of understanding the correction more intuitively without the need for algebra like in the first explanation. So you basically only need to take the first hurdle, which is the different formula, but from there it is quite easy. I will throw it at you and then explain it. The core idea is that you can use all pairwise differences between values instead of the squared distances to the mean when calculating the variance, and I will show you an example in a minute. What you are doing is calculate all possible pairwise differences and then divide the result by twice the sample size squared. Why do I introduce another weird looking thing in the denominator? It will make sense in a second, I promise. Let's look at a picture for that procedure first. This is the situation we had before. The square differences to the mean arranged in a column. Now, because we want to calculate all squared pairwise differences, we will extend this table, or matrix if you like, and put the data in the first row as well, instead of the mean. Now, according to this formula, to get the sum of squares, we start with the first row and calculate the distance of the value in the first row 3 to all values in the columns, which is basically the whole population. Let's first add the indices to the table. The first value is 0 because it is the same data point. The next is the squared difference between the first two values, 3 and 5, which is 4. Then 25, then 4, then 36, then 16, then 1. You see, it is basically the same procedure as we've seen before when calculating variance using the sample mean. You do the same with the second row, and then with all following rows until you got all the rows and columns. Great. This is a table with all squared pairwise differences between all data points. What is here to notice? First, the matrix is symmetric because we calculated each pairwise difference twice. For instance, you calculate 5 minus 3 squared and 3 minus 5 squared, and both end up on opposite sides of the diagonal. Because of the square, the sign is always positive. Second, the diagonal is all 0 because the formula also includes the distance of each data point to itself, which is 0. To get to the variance, we have to calculate the average value. In this case, we don't have to divide by n, but n squared because we have n times n values in our table, not just n values as before with the formula involving the mean. Next, as discussed, each value is in here twice, so we have to additionally divide by 2. If you plug in all the values, you will get the exact same value as before, which is 8.29. Cool. Now that we discussed how this formula comes to be, we can come back to our n-1 problem. Remember that it was all about samples. So what does it mean to draw a sample in this table? It means to only look at a small part of that matrix. To make it easy, we can just take the first 3 values as the sample, 3, 5, and 8. Just using the formula depicted here to calculate the variance is the equivalent of using the sample mean and n in the denominator before. It will lead to an underestimation of the variance. Can you spot why that is? Without actually doing the math, the reason here is the ratio of diagonal to off-diagonal values. Remember that, by definition, the diagonal must be 0. Look that for this sample we have 3 diagonal elements and 6 non-diagonal values. So 1/3 of all our squared pairwise differences will always be 0. In general, this is true for n out of n squared cases, which is 1 divided by n. You can see that with each new data point we add 1 0 to the diagonal, but 2 times n-1 fields with pairwise differences to other data points. In the full matrix, the population, this ratio is 7 out of 49, which is only 1/7. This means that in the sample case, the zeros have a much bigger influence than they have in the population. Roughly spoken, the sample is more similar to itself than to other values of the population. If that reminds you of the first part where we saw that the sample is usually closer to the sample mean than to the population mean, great, because it is the same thing in disguise. Here I highlighted the differences to the other data points of the population in green. The differences within the sample are still the 9 squares top left. You see that the green fields don't include any zeros, so when you take the average of these green fields, it will be bigger than the uncorrected average of your sample, which is the sum of them divided by 9, because they don't include the within sample zeros. That we have to divide both by 2 does not make a difference, so we need a correction. How does that look like? Well, you basically ignore the fields with zeros when you calculate the average of the squared pairwise differences. In this case, instead of dividing by 9, you would divide by 6. In the general case, you will have the diagonal zeros in 1 divided by n times of all cases here in gray. This means that in 1 minus 1 divided by n times of cases, you will get the off-diagonal pairwise differences, which don't include the zeros and which are the unbiased expected squared differences here in green. How does that look like as a formula? You replace the n squared by n times n-1. There we have the n-1 again. Because the unbiased differences, the ones not including the self-differences, occur with a proportion of 1 minus 1 divided by n, dividing the original biased estimate by this term, which is the same as multiplying by n divided by n-1, eliminates the bias. You might see that this is the same correction factor we arrived at in the first part, which it should, because it is just a different angle of looking at the same problem. So, as a short wrap-up, the correction of n-1 in the denominator if you don't have access to the population mean serves to eliminate bias in the estimation of the population variance. It looks like you would ignore one of your data points, but does not. We saw 2 different intuitions what the n-1 means. In the first example, it stemmed from the fact that the variance estimation is too low and that this difference equals the variance of the sample mean. Because this equals the sample variance divided by n, the correction factor needs to include this n-1. In the second case, it stemmed from the fact that you will get proportionally too many zeros due to including the differences of the sample data points to themselves. The correction thus involves calculating the average without these, and because they always make up 1 divided by n of your sample, you divide the estimate by 1 divided by 1 minus n, which is the same as multiplying with n divided by n-1. And that's it. That is why the formula with n in the denominator is biased and why n-1 is the correction to this bias. Note that it is most impactful when you have small samples. Also, the standard deviation, which is the square root of the variance, is not unbiased by this procedure, and that unbiasedness is not always the most important aspect, so you might sometimes find applications where a different correction just suits the purpose better. However, this is a topic for a different video, so thank you for watching and I hope you found this helpful.